Hey everybody, welcome back. So in this video, we're going to talk more about the theory of quantum mechanics, treating a particle as a wave. And what we're going to focus on is the so-called wave function. So, let's consider a particle traveling in one dimension. So we'll just talk about one-dimensional motion. If you go to 3 dimensions, the math gets a little bit more complicated. So we'll save that for upper level quantum mechanics class. But for our introduction here, let's just consider something traveling in one dimension. We'll call it the x-axis. So in the so-called classical or particle picture, this object is traveling, let's say it's going to the right, and again, we'll just call this the x-axis. So it's traveling like that. It has some mass m located at some point, the center of mass, with some velocity v like that. Treated as a wave, this thing, this object, this collection of matter is some sort of matter wave, right? And again, I don't know how to really represent that other than put some wiggles here. So I'm not suggesting that it's still a point particle riding a roller coaster going up and down. What I'm suggesting is that this particle is this wave, this matter wave. The wavelength given by de Broglie is h over its momentum. So how do we actually describe this wave? Well, that's going to be described by the wave function. And conventionally, we use a capital psi. So this wave function, it's going to be a function of 2 variables, x and t. The idea being, just like a traditional wave, a classical wave, like a wave on a string, or an electromagnetic wave, the value of psi at some x at some time is going to be the value of this function. So for instance, this picture up here, this might be a snapshot of psi versus x at some time t. Okay, so it's going to be a function of two variables, position and time. Now, the theory of quantum mechanics that is developed says that knowing the wave function is very valuable because you can do things with it, but the wave function itself doesn't really represent anything physically. In fact, mathematically, this wave function can't even be a complex values or a complex function. Physically, though, you'll get something if you take the square of this wave function. And that's what we want to talk about. We're going to talk about some properties of this wave function and how do you get some physical information from it. So formally, the probability, and we'll discuss more the idea of probability in just a second, but let me just define this. The probability of locating the particle between position x and position x plus some tiny dx. So you can see that this looks like calculus might be involved. So dx just represents some very tiny delta x, right? A tiny, tiny distance. So the probability of locating the particle between position x and x plus dx at time t is equal to this probability. What you do is you take the square of the wave function at position x at time t, and then you multiply by that tiny distance dx. Okay, now a couple comments. First of all, I put down what looks like absolute value signs, right? And then I squared it. Actually, that's the modulus. Okay, if psi is complex, if it's a complex function, you guys may have had some complex math. If you haven't, don't worry about it. But formally, if you have a complex function, what this represents is the product of the complex conjugate with the function. The complex conjugate is symbolized by this little asterisk. And what that means is, right, if you represent the values of the function in complex form as a real part plus I times the imaginary part, B. So if the value of psi at some x and t can be represented like that, so this is the value of psi at some x and t, the complex conjugate means you just replace I with minus I. Okay? That's what it means. So now it could be that the wave function is not complex. It's just real valued. Then you would just take the regular square. Okay? But I put these signs here, these bars, to represent that it could, if it is complex, it means to multiply by its complex conjugate. Okay. Another note is, if you've had any probability, if you've taken probability, you might recognize this. This is the definition of a probability distribution function. So psi squared is a probability distribution function. So if you multiply by some infinitesimal distance dx, you'll get the probability that the function, right, or I should say you'll get the value of that probability at x to x plus dx. You'll get it over some small range of values. Okay. Our function is a function of two variables, so this would be the probability at some time t of locating it between x and x plus dx. Okay? All right, so that means then if we do this, let's say that we do this, we're going to sum up the probabilities. So we're going to sum up the probabilities between two values of x from a to b. This is going to be the probability of locating the particle between what? Between x equals a and x equals b at time t. Okay? So that's what we mean by this probability density function or distribution. It's a continuous distribution. Okay? So notice this does assume something though. And it's what this equation or definition assumes is what's called the normalization condition. So what do we mean by the normalization condition? That means this, watch. If I write down this integral, minus infinity to infinity of psi squared. Right, so what am I asking with this integral? What I'm asking is, what is the probability of locating this particle between x equals minus infinity and x equals plus infinity? Well, if there's a particle, it's got to be between minus infinity and plus infinity. So this probability is 100% or 1, because we usually, right, we use decimals. This is known as the normalization condition, that this integration has to give you 1, okay? And in practice, what that does is, if you demand this condition, that's going to force you to have a certain coefficient to your wave function. Okay, so this definition up here assumes that the normalization condition is met. Okay, all right. So now don't worry, we're not going to be doing any integrals. Okay, or maybe you're disappointed. I don't know, but we're not going to be doing any integrals in this class. But I do want you to know that mathematically there is this wave function that describes the actual matter wave. It's the square of the wave function, though, that means something physically. The square is this probability density function or distribution. And using this probability distribution, you can find probabilities of locating the particle. Now let's talk more about this idea of probability, because this is inherent in quantum mechanics, treating particles as waves. It's related to the Heisenberg uncertainty principle, right? This whole idea that you can't talk about where a particle is with 100% assurance, 100% certainty. You can only talk about probabilities of locating the particle in a certain region. Okay, so if you think about how the interference pattern is built photon by photon, right, in the double slit experiment, or you think about how the diffraction pattern is built electron by electron when electrons pass through a foil, right? The individual electrons have probabilities of showing up at certain points on the screen. And that is inherent in quantum mechanics. And it's all due to the fact that treated as a wave, the particles are spread out, right? There's some spatial extent to the wave. So pinpointing exactly where a particle is, right, you can't do it with 100% certainty. You have to deal with these probabilities. This bothered a lot of physicists when quantum mechanics was being developed. In fact, Einstein famously never really was happy with this whole idea of probability of nature. All we can say is there's a probability of locating an electron somewhere, for instance, right? That really bothered him. There's a famous quote, and I'm paraphrasing, that he said, God doesn't play dice with the universe. So, and he tried and tried to argue that if you know enough information, you should be able to determine where a particle is going to be with 100% certainty. But nowadays, the conventional interpretation of quantum mechanics is that this probability is inherent in nature. This is the best we can do. Okay, now, with that idea of probability, there are some other things that have to be true about this wave function. And let me show you guys. Let me sketch a probability. Whoops, I'm so sorry. Wrong window. Let me sketch a probability distribution here. Let's scroll down. So a way to graphically represent what we just described above is if I make a plot, let's let this be the x-axis. And what I'm plotting here is the actual probability distribution function or density function, psi squared. Now again, this would be at a certain time t. It may look something like this. I don't know, to just go like this, right? And then it's going to peter out there, and maybe it'll go like this for some arbitrary wave function. Okay. All right. So first of all, if I put this is x equals a and this is x equals b, notice that graphically the probability of finding the particle is just the area underneath this curve, because that's the definition of the integral. Also realize that the normalization condition, if I integrate the probability distribution psi squared from minus infinity to infinity, I'm going to get the area underneath this entire curve. So the area underneath this entire curve has to be 1. That means that psi, the wave function, it has to go to 0 as x goes to plus or minus infinity, right? If not, you would have this wave function, right, going off like that. So the area underneath psi squared is going to be infinite, right? That can't be physically. So one of the conditions on the wave function is that it has to go to 0 as x goes to plus or minus infinity. Another condition is that psi has to be continuous. You can't have kinks in it if it's going to represent a probability distribution when you square it. And also, this isn't as obvious, the derivative of psi, this is really a partial derivative of psi with respect to x, also has to be continuous. Okay? Actually, that's I misspoke. This is why psi can't have kinks in it, right? Because then the derivative would be discontinuous. Psi continuous means it just can't jump from one value to another value. All right, but these are additional conditions on your wave function. Okay, so look, what I want you to know, it's in the summary notes about the wave function, summarized right here in this section of your summary notes. Okay, so just know those things. Now in the next video, we'll talk about, how do you actually find this wave function for a matter wave. Okay, and we'll develop what's called the time-independent Schrodinger equation. But that'll be the next video. And look, I realize that this quantum mechanics stuff, particularly here and the next video and the one after that where we do an application, it's going to be very mathematical. That's the nature of quantum mechanics, okay? So just giving you some warning there. But we'll develop the Schrodinger equation in the next video. Okay, bye-bye.